Hi, we are the group 44. I'm Christopher and I'm going to explain how we plan, develop and test the leader rotator. So we have the phase 1 that we do in P10, and the next step are implement the LCD in the circuit that is here, put in the number of rotations that the lead do, and for do that we have the same timing diagram, and we now implement the LCD printing new message counting the rotations of the circuit. So for do that, in the microcontroller, we connect the port D at to the LCD for print message in ASCII characters, and for do that, in the C code, we use a bar LCD flag to notify that when we need to print a new message with new information. We have the same state diagram now with the bar control rotations that counts the number of rotations that we do in a cycle to all of the states and all the leads. So when we do a complete rotation, bar counter rotations go up in 1 unit. So the next step is to see to implement this idea in the C code. Now in C code we can see that it's the same code that we have in the P10, but now we are adding these new variables that are bar counter rotation and the converter in ASCII characters, and the bar LCD flag that notify us when we have new information to print in the LCD. We have the main loop that are the same in P10. In the init system, we change the port D to use the LCD, and in port C we have all the LEDs. So now we start in bar LCD flag to start the printing in 0 rotations, and the bar clock flag that are the same, and the bar counter rotations starts in 0, and we init the LCD. In the output logic, the code are the same that in P10, so it have no changes in all. So here in the output logic, we have the if bar LCD flag is 1 in the state 0, it means that it complete a rotation. So we convert the barcode rotations int in a ASCII character. We clear the LCD and we put the rotations in the LCD, and the bar LCD flags turn 0 and barcode rotations go 1. So when we complete in rotations in left or right, we know that bar LCD flag is going to be 1 to print new information. So in Proteus, we have this circuit connecting all the LCD ports in the port D, and all of we have in the P10 are the same. So we start the simulation, and we can see that the counter of rotations is increased when we put master clear, the clear direct. It starts from 0 again, and rotations goes high, And the same concept, it's here when it turns left, the number of rotations going high. In watch window, we can see the variables that are used in the microcontroller. So we clear direct and we can see the bar LCD flag stays 1, and when it's arrived to S0, it turns 0, and when count enable is 1, once it's 0, the count rotations are able, and when count enable is 1, you see that it stays here and the leader rotations don't change. So for every rotations, the counter rotations increase in 1 unit, and printing this new message for the next rotation. And we can see that this value is going high. So that is the leader rotator using the LCD. And now Fernando is going to explain how we add the timer 0 and timer 2.
Good afternoon, I'm Fernando Pincay. I'm going to explain how we implement the timer 0 in the LED rotator timer 0. So we're going to generate the period timing using interrupts from internal timer peripheral timer 0. We're going to modify the hardware and delete the external clock input and program the application configuring the timer 0 to generate the bar CLK flag that is going to work with 100 milliseconds, that is the same as 2.5 hertz. So what's happening here? We are deleting this clock signal and we're replacing by this bar select flag that is going to be generated by our timer 0. So let's see that we are going to place our software. We're going to place the timer 0 configuration in the init system. So in this way, the whole software doesn't change. In the only thing in the program, in the software, will change will be the select a flag that instead of coming by the external clock is coming from the timer 0. So we represent it here in this way. So we use the state logic as before, but this select a flag is the one coming from this hardware software diagram that comes from the timer 0. So here we have N1, N2, and N3 that are values that we are going to calculate in order to obtain the period frequency before set. So how we configure it? We have this TOCS will be equal to 0 because we want to select the frequency oscillator divided by 4. We have a value N1 loaded by the T0 PS that will be 16, or sorry, 011, and 2 and N3. So once this time measure interruption flag happens, the post scalar is lower, and N2 value is calculated by the boost minus this value. So the two things that we add to this software is in the init system we place the timer 0 configuration, and in the ISR function um, we place this algorithm in order to detect the interruption flag of the timer 0. So let's see how our project works. So we have here the timer 0. So this is the software for the I interruption service routine ISR function. So we see here that is loaded the timer 2, the timer, the N2 of the timer 0, and this is the way it works. So in the init system we enable and load the timer 0, load the values of the timer 0. So N1, N2, and N3 enable timer 0. This is the N2 calculation. So we go back to the internet interrupt service routine, and we see this variable here, bar timer flag, that is will be in our software, the one that is coming to our state logic. So this is how it works. So let's clean and build it. We go to our, well, let's wait, it's loading. We see some deprecated things, but not our interest. We're interested in the location. Let rotator, timer 0, let rotator. Let's see. This is the timer 0. Let's open, I think it's this one. Let's check it. Yes, timer 0. We can see here. So child sheet. Let's load our value. Our cuff is 12, 1221, 1222 is the last one. Okay, parent sheet, and we're going to debug in the CSD style. So we're going to put a breakpoint when the when the state logic is goes into the current state. So in this way, an elapse of 400 milliseconds would be loaded. So let's check it. So let's see the variable here and run it. We can see here that 466, but this is because um, we have to be able to set the this breakpoint in some point that is exactly 400 milliseconds. In this way, this breakpoint should be placed in, should be the total sum of all the times that the bar time flag is equal to 1. So this is an estimation, but in this way we can load again. 450 milliseconds is going less. Let's run it again. 415, 415 elapsed time. So in this way is working this timer 0. Let's see the timer 2, that is the enhance of this timer 0. But this timer 2, the only thing that changed in this hardware software diagram, the remarkable thing would be the we have, instead of having 3 values, we have 4. So as before, we have 16, 215, and 100. The easy way to going is separated by 10 multiplied by 10, and it's 100. So this is the hardware software. This is important in order to implement the interrupt service routine, but it's the same as before, the procedure. So we have our project here for the timer 2. Let's go to the source file, let rotator, and here we have the software. In the init system function, we are here. We enable the timer 2, enable the load the values of n1, n2, and n3, and n4. Let's go to the interrupt service routine. We have here our bar timer flag that is going to be changed in the state logic. So let's clean and build the project. It's loaded here in timer 2. Sorry. It's loaded and build it. But in this case, let's go to the P12 timer 2. Let's open this Proteus. are in timer 2, load cough. Okay, and let's run it as before. Running the CSD style, looking variables, and here I will be more uh, accurate with these variables. So let's put the breakpoint in here. So let's run it. Elapsed 400 milliseconds. 400 milliseconds, and this is how it is working, right? So thank you very much. Buenas, soy Fernando Pincada, voy a explicar el timer 0 y cómo lo implementamos en la fase 3